Okay, so good morning, everyone. Welcome to today's TSU Present Online Seminar. I'm Ren Kaixu from the TSU. So it's my pleasure to introduce our distinguished speaker, Dr. Petr Pokorny from the NASA Goddard Space Flight Center. So here is a brief introduction to Dr. Pokorny. So Dr. Pokorny is an accomplished astrophysics physics with the background in physics and astronomy from the Charles University in Prague. So where he also earned a PhD in theoretical physics. So his research spans various global institutes, including the NASA Goddard Space Flight Center, and the focus on the formation and the evolution of interplanetary dust, the origin of circular dust ring, and the application of machine learning technique to detect impact crater on airless bodies in the inner solar system. So today, Dr. Pokorny is here to talk about the automatic detection of lunar crater using machine learning techniques. So he will be showing us how deep learning algorithm can be used to automatically detect the impact crater on the moon, and something that was once too overwhelming to do by human hands. So Dr. Pokorny will also explain how this technique not only make it easier to catalog a lunar crater, but also open up a new possibility for finding craters on other planets. So this presentation will give us some valuable insight into the latest advance in automated future detection across our solar system. So please, Dr. Pokorny.
Thank you for the introduction, and it's a really pleasure to be here. So let's start. Let's start with what machine learning actually is. So if you look at Wikipedia or something like that, encyclopedia, you realize that machine learning is just a field of study in artificial intelligence, and its main purpose is to learn from some data and generalize the knowledge to unseen data, and then perform tasks without explicit instructions. So effectively, what you are trying to do is to teach some artificial intelligence to think like you. And it was originally coined in 1959 by Arthur Samuel from IBM. And his first motivation was to use machine learning or AI for gaming. So he wanted to play a game of checkers, and he was lacking computational and resources, and his memory was too small of his computer. So he needed to do some computer magic to be able to play against the computer checkers. And that's how everything started. Today, we use machine learning almost everywhere. So we have these large language models, that LLMs, that are represented by ChatGPT or Claude or Gemini. We use it for speech recognition, for object detection, or time series forecasting. And effectively, the two main objectives of machine learning is data classification. So you can see on this little image here that you want to distinguish in the image humans, dogs, cars, and other things. And the other objective is future outcome prediction. So you want to predict how some certain functions will evolve, or with that, you can create images like that you can see with, for example, DALL-E or Midjourney that are used extremely well today. So why do we need machine learning in science? As you might know, the amount of data that is in numerous fields is overwhelmingly larger than the number of skilled specialists. So even in astronomy, we have so many data sets and only so few people that can actually look at them and know what to look for. Example from medicine and protein structures. So you can see on the right side an image of a protein structure. And in the last 60 years, humanity identified around 170,000 proteins, their structures. But we know of 200 million proteins, and we didn't have structures for them. What Google did with AlphaFold, they trained their AI and their machine learning on 170,000 proteins that were known, and they revolutionized the entire field and effectively predicted the structures or potential structures of all 200 million proteins. And they made everything publicly available. this also yielded a very highly cited research. So this was really one of the key points, key turning points in that field of science. And we can have something more closer to us. So, for example, Messenger and LRO are two spacecraft that mapped Mercury and the Moon, respectively. And these spacecraft delivered hundreds of thousands or maybe even millions of images that can have resolution down to 1 meter per pixel from LRO NAG, for example, on the Moon. So if you do simple estimates and calculations, you can get, maybe you can even detect 50 million craters on Mercury and more than 1 billion craters on the Moon if you really go with this super high precision and scan the entire surface. And imagine you would take 5 seconds per one crater. You would look at the image and take 5 seconds to identify one crater. It would take you 1.4 million hours just to go through that billion craters, which is around 700 work years. It's an immense amount of time that nobody can devote to this one task. And then you imagine that data changes and you have to do it all over again. So just this is very overwhelming. So to show you how it looks like, this is a little teaser of this talk. So on the left side, you have a human being trying to identify craters. On the right side, you have AI doing the same task. You can see they are almost on par of each other, but if you notice on the top, there's a time that takes each of these two individuals or entities to do their job. As you can see, the human took almost 3,000 seconds to do identification of these. There are around 1,000 craters here. On the other hand, the AI took 15 hundredths of a second. So that's 50,000 times more time that you spend as a human being on this simple task. And imagine you have to do it for the entire surface of the entire Moon, for example. So it's a very demotivating task. So how did I get to machine learning, actually, and the object detection itself? So in 2023, we were investigating origin and dynamics of the circumsolar dust ring near Mercury's orbit. It looks something like this. So you have Sun in the middle, and then orbit of Mercury is in this dashed line, and then there's this dust ring. This is from a model that's covering almost the entire orbit of Mercury. So we had a paper published about that, and what we found out that we can only create this dust ring by an impact that was quite recent in the last 20 million years that created quite large crater, larger than 40 kilometers in diameter. And so I was thinking it must be super easy to just go to Mercury, take the data set of all craters and their ages and just find the most viable craters, but there was no database like that. So we had to do manual inspection of all these potential craters and try to find the dates and figure out which of these craters are actually potentially very young and recent. So that's how I got to machine learning myself. So before we start with machine learning and on the Moon, I wanted to show you some of the manually derived impact crater catalogs that we have on the Moon. So it all started with Het et al. 2010, who did one of the first papers about the human-driven catalog of the Moon, of craters on the Moon. And they were focused on global distribution of large lunar craters. You start big, and then you add smaller and smaller craters. So they focused on craters larger than 20 kilometers. They found over 5,000 craters. And they used the digital terrain model from the Lunar Orbital Laser Altimeter on Lunar Reconnaissance Orbiter. On the right side, you can see a figure from that paper, and you can see the distribution of those craters. It was really important work in this field, and it allowed a lot of great science. Then 8 years later, there was sort of like a successor of this work by Pavlidis et al. 2018, and they effectively expanded the Het work by going to small diameters down to 5 kilometers, and then expanded the work by 14,000, 15,000, to 22,000 craters, actually 17,000 craters more. And then next year came out a data set from Robbins, 2019, and he focused on craters down to 1 to 2 kilometers. So this paper came out with more than 2 million impact craters, with 1.3 million craters having diameters larger than 1 kilometer. So you can see, again, the plot from this paper on the right side. And at the time, and to my knowledge, until today, this is the most abundant manual crater database on the Moon. it must have taken immense amount of work to get all these craters to this catalog. So here's a little comparison with, in 2019, from Robin's paper, of different catalogs from different sources and how they fare well with respect to the Robin's database. That's 2 million craters. So you can see that below 3 kilometers in diameter, there's almost nothing. The fraction of craters is 0. And it sort of increases for multiple sources, and then around 20, 30 kilometers, you can see nice agreement of most of those works, except for Losiak that has underreported a little bit, even the largest craters. But for example, Wang et al. 2015, that used more automated methods, overreport craters that are larger than 100 kilometers. So it's very interesting that different methods yield you quite different results. And this is sort of starting the machine learning era around 2018, 2019. So now I would like to focus a little bit on machine learning papers that came out in the recent times. So until 2018, 2019, most of automated crater classification methods had one major issue. Despite performing well on training data sets that the authors picked, they didn't perform well on unseen data. So if they trained some algorithm on some little data set and they used it somewhere else, it didn't work well. If they tried to use it on a different planetary body, it failed as well. So for example, Salomonichar and Loncharich 2014, they used hybrid method that used Hawk transformations to reconstruct topography on the moon. It worked well on their data set, but then they tried it somewhere else, it didn't work that well. Emam in 2015 used a different method, edge detection, which is great for extraction, different features on the lunar surface. And again, the same problem. Stepinski 2012 used decision trees, again, another different method. They didn't work that well. There are a few papers that use neural networks like Wetzler 2005, Cohen 2016, or Palafox 2017. But again, they didn't achieve the generalization that would allow them to use that method on unseen data. So then that takes us to Silbert 2019, who used deep learning for lunar crater identification. Deep learning effectively is one of the parts of machine learning that learns from itself. And they use the DEM, the digital elevation model, on the moon with a resolution around 59 meters per pixel. And the reason why they use the DEM is that the crater appearance in DEM is independent on the incident sunlight direction. So you have a plot from that paper on the right side, and you can see that the blue circles are the manually detected craters that were reproduced well by their method. They have also red circles that are the new detections that were not signed by humans. And then in the bottom part, you have purple craters that are craters that the method missed. This work used a convolution neural network called UNet. And you might know UNet from other things like image generation models, DALI, Midjourney, or Stable Diffusion. So it's a very well used architecture that's been profoundly used in many different fields. But in Silbert, they focused on smaller regions of DEM, so they didn't do the entire moon. And one of the findings was that they had good extraction of smaller craters, 15 or less pixels in diameter, but worked quite poorly for large craters than 15 pixels in diameter. So for large craters than around 1 kilometer or larger. What was great about this paper is that they successfully tested it on Mercury and made effectively a big step in generalization. They trained it on the moon, and then it fared well on Mercury. So that was a great step forward. And also they made it available on GitHub, so you can download it and try it for yourself. So before we go any further, I would like to talk a little bit about convolutional neural networks. Just very simply, one slide, what it is. So convolutional neural networks are deep learning neural networks that are well suited for image classification or object recognition. It's perfect for identifying craters or boulders, hollows, anything you want on surfaces of planets and their moons. And they effectively consist of three main parts. a convolutional layer that extracts features from the input image that you put. So you have the zebra here on the left. Then you have pooling layer that reduces the spatial dimensions produced by the convolutional layer. Effectively, it reduces the complexity of the task and tries to retain as much information as possible. And then there's the activation layer that applies some nonlinear functions to the pooling layer to allow the machine learning. So then you go to the flattened data set, and then on the right side, the classification is the neural network itself. You see how these neurons are interconnected and they have different weights. And then the output is some weight function that gives you the probability distribution. It's 20% horse, 70% zebra, 10% dog. So this is pretty much how it works in a nutshell. It's a little bit more complicated, but let's keep it at this level for now. So following Silbert, we have also Wang and Wu, who used active machine learning, and they effectively combine the planetary imagery and the digital elevation models. So they get more information because the images themselves, they have higher resolution, and they use the DEM, the digital elevation model from Celine Cayuga terrain camera, and then also use the Lola altimeter from LRO. And what they did something really smart. They used iterative approach that effectively, in every iteration, labeled images that they used, and they had more craters that they could train the machine learning on. So in every iteration, they had more and more training data. And they also used these 3-component classifier, highlight features, adaptive boosting, and cascade. Effectively, these methods are quite standard in machine learning. And they successfully deploy on the Moon and also on Mars. On Mars, we have also very high resolution data, so it was great. It was, again, generalized to 2 planetary bodies. And they reported quite low false positive rates, so they were detecting very high, with a very high precision, the craters on both bodies. But in total, they had around 7,000 craters on the Moon and 1,200 craters on Mars. So it's nowhere near to the level of Robinson, who has 2 million craters. Then it was Ali Deep, 2020, and they wanted to focus more on retrieval of crater shapes. So they focused on crater ellipticity. And as you can see from the figure on the right, they did quite well. They have crater ellipticities and a wide range, and it can even compare Highlands to Maria. So it was a really great paper about that. It's effectively some sort of successor of Silbert 2019. They're also using digital elevation models from Lola. And they use this network called Mask RCNN. And the great thing about this network is that it produces a polygon mask that you can then fit by an ellipse. It effectively cuts out the crater, gives you all the pixels that the crater represents, and then you can quite easily fit it with an ellipse. And it gives you much better shape determination. They also increased the detection image resolution, which was one of the problems in Silbert. So, and they were able to recover almost 87% of Latest 2018 craters. So they had around 22,000 craters, and they also recovered or found 40% potentially new craters on top of that human-driven crater database. So in total, they have 30,000 craters down to 5 kilometers, and it was really great. But it's still, they are missing the much more craters that are much more numerous. The last paper I wanted to show you is Fairweather 2023, and they focused on deriving model ages, and they used only images. So no DEMs, just plain images, which is proved to be much more difficult. And as you can see, they focused on several areas on the Moon, so it was not a global search or global assigning of ages. And what they used was this framework called You Only Look Once, YOLO, version 5. It's also a convolutional neural network. And it was very localized, so no DM, as I said before. And what they did, they built on their previous work from Bendix 2020, Allegheny 2021, 2022. They detected more than 90 million craters on Mars. So you can see that on Mars, there was already a lot of work done with machine learning-driven detections, and they had more than 90 million craters on Mars. So they tried to transfer it to the Moon, and it was very successful. And they had very good agreement with manually determined ages. So somebody did the crater counting and they compared it with their automated methods. And they also noticed that the secondary craters provide quite extra complexity because it's very difficult to distinguish between primaries and secondary craters. So what do we find from these published works? What are the basic findings? So first, that many different methods were successfully deployed on different lunar crater datasets, lunar datasets, images, and DMs. But we can see that the vast majority of these datasets is still unexplored. We have so many different datasets now, and all of these craters are waiting to be detected. So using digital elevation models makes the data preparation easier. So those used in Silbert or AliDeep. You have no problems with the illumination conditions. The image quality doesn't change much, so you have no problems with noise or shading, slopes, anything like that. The DM is usually perfectly aligned, so you know where the craters are. And it also contains crater depth information, which is a great thing to have if you want to check, for example, for other features. But the problem is that you are using process data, so it usually has smaller resolution, might contain some local inconsistencies, and getting very high precise DMs is quite impossible at the moment. That's why they usually use the DMs with much smaller resolution, around 60 meters per pixel. Then we also saw that individual images can be successfully used for the crater detection, like in Fairweather papers. And you can go much deeper. You can go to small craters that are tens of meters in diameter. It's computationally possible with several GPUs, which is great because you can do it almost on your personal computer. But problems with this is that images are usually noisy. They are sometimes not geolocated. The illumination conditions change, and analyzing large areas proved to be quite challenging. But it can be done as it was done on Mars by Legay in 2022. So now I would like to focus more on an example of how crater detection on LROC NAC images works. Show you how to go from having almost nothing to something that you can be quite happy with, some final product. So first we have to start with collection and pre-processing images. LROC NAC images can be found on Planetary Data System that is run by NASA, or Space Exploration Resources Data Portal that's run by the Arizona State University. So you go to PDS, you can download any image you want, everything is publicly available. Then you need to map project and georeference the images, because these images are usually not georeferenced if you take the raw data. So for that, you can use USGS integrated software for imagers and spectrometers, ISIS. That's also publicly available on this website. You just have to learn how to use it, and that effectively makes your work much easier because you don't have to make your own codes for this, and it's not that difficult to use. Then, since you have a spacecraft, you need to know where the spacecraft is, what is the pointing direction. So for that, you can use SPICE. SPICE is also publicly available. It's also available on NASA website. And effectively, for each image, you will figure out where the spacecraft was, where it was looking, and make the image geometry the way you need it for your detection. And lastly, it's very useful to use geotiffs for this type of works because they are easier to handle and they contain all the information you need. And for that, you can use Geospatial Data Abstraction Library, GDAL. That's also publicly available and it's very easy to use. And then effectively, you combine all these together and you get some sort of pipeline. If you are lucky enough, like I was, the pipeline is ready so you can get already these pre-processed images without any cost to you. But everything is publicly available, so there should be no problem for you to do it as well, even if you're just starting with it and you have no experience with this. Everything is very well documented, and I really encourage you to check those websites at least and see what they can do for you. So now you have your images and you processed your images and you need to somehow train your neural network. So that means that you need to select some data set and some images. So these images should represent some different geological features and terrains that you want to investigate. If you want to focus on craters, you should focus on different types of craters that you might detect in your data set. If you want to focus on highlands or mare, you have to have data sets from there. You cannot just teach the network, the neural network on one data set and then hope that it will somehow learn how to detect craters that are completely incompatible with what you taught it. You have to also select a variety of illumination angles and lighting conditions. So if you are dealing with craters that are lit with very shallow light, like something on the pole, you need to feed it. The training data set should be consisting of these craters. You should not be using craters that are on the equator that are very lit, almost with a 90-degree illumination angle. So sometimes it's beneficial if you are dealing with different lighting conditions to separate your data set into two, with shallow illumination and very steep illumination angles. So for example, you can have your own model detection for shallow illumination angles in the polar regions. And then the funny part comes when you have to label your training data set images. So what we were showing at the beginning in the video, you have to go to your images and label every single crater that you can see. Effectively give it a bounding box or bounding circle or bounding ellipse. And you should do it to some limiting size. So it's usually 7 to 10 pixels, depending on different sources and different scientists. They never agree what the limiting pixel size is, but something around 7 to 10 pixels is quite well. There's an agreement that should be something like that, the limiting size. You can do it manually, or you can speed it up, this process, by using some pre-trained neural networks from your previous work or from some other works. It can be beneficial because it can speed up your labeling really, really well if you don't have much bad data, or if the detection method doesn't omit a lot of craters. But it can be also detrimental if you detect way too many non-craters and then you have to remove them manually. That also can slow you down. And usually the sizes that we use for these training data sets are around 416 by 416 pixels up to 1024 by 1024 pixels. Why the size range? The size range is usually limited by the highest resolution is limited by your memory, so you need to feed it in some. It depends on what system you have. If you have big and fast GPUs, maybe you can use bigger images. It takes a lot more computational power to deal with these larger images. The smaller sizes is about the efficiency of the network itself, about the amount of detail that you can actually have in those training images. So they should not be super small, because then you cannot train on larger craters, and it can make it much more difficult to actually successfully deploy your detection model. So imagine that you end up with 10,000 distinctive craters. I'm showing you here, this is the labeled picture, and there's 1,000 craters in this or so. And then you imagine that you have phase space that you have to cover. So you have solar azimuth that can go from 0 to 360 degrees. And you have solar elevation angle, can be from 0 to 90 degrees. And then you have crater size from 5 to 1,000 pixels, let's say. And if you even crudely sample this phase space, 360 degrees times 90 degrees times 50 sizes, you end up with 18,000 potential combinations. And you don't even have that many combinations in the data sets. And there are much more. The phase space is much, much bigger. There's different geological conditions, crater maturity, complex and simple craters. So you end up with overwhelmingly large number of combinations that you have to cover with your training data sets. So there are two solutions to it. One solution is to get more craters, so you can label more and more and more, but that's very detrimental. And you can get around it by enhancing your training data set by some transformations. Luckily for you and for everybody else, there's a thing called data augmentations. So there's this open source library for data augmentations called Albuminations. And one of the examples is here on the right side. So it's implemented in most modern objection detection models. And what it can do, it can rotate, mirror, blur images, add noise or subtract noise, change color grading, stretch images, add perspective, and other things. And it effectively enhances and generalizes your trained data set and allows for your neural network or a detection algorithm to perform much better. And the performance metrics are going through the roof. So initially, you can start with 1,000 training subjects, but if you apply just rotation, some noise addition, and some color grading, you can end up with millions of combinations that will well cover all potential combinations that you can that you can approach with your machine learning model. One problem is that it cannot simulate the physical phenomena. So if you have only simple craters, it will not create complex craters for you. So this is one of the drawbacks of this, but it's still, it disenabled so much more generalization that we had before. So your next step is you have to select some object detection model. So as I showed before, there are different detection models, and on the right side, you have an image of comparison of 12 different detection models from different sources. And the plot effectively shows you the number of parameters, so it is the complexity of the network. On the x-axis and on the y-axis, you have object detection. So the ideal network would have as few parameters as possible and as high object detection precision as possible. So you would want to be around 10 million parameters and 56% or even higher. And you can see from this plot that the networks are not that different in their performance. They are getting better and better. So this YOLO V8 or V9, it's for the same amount of parameters, it gets much higher precision, the object detection precision. So to name a few of these detection models, so we have the YOLO family from Redmond 2018. So they are mostly used version 3, version 5, version 8. Now version 9 is the newest one, if I remember correctly. There's also EfficientDet, RetinaDet, faster RCNN, so it's regional based convolution networks. Then you have mask RCNNs. And each of these networks have its pros and cons. They have different setup, different architecture, so they can be fast, but not very precise. Some of them can be complex, very precise, but very computationally demanding. So you have to sort of either test different detection models or learn about a little bit more what the best is for your concrete approach. So for our LROC images, I selected YOLO V8. YOLO V8 is great for the object detection. It's used for real-time object detection in many different fields. And it's really great for creating bounding boxes of different objects like cars, animals, and craters as well. And I created trained data sets of 30,000 craters across 160 images. Each of those images is 512 by 512 pixels. And then with these 160 images, I had to separate them to 3 different subsets. So one subset is the training data set itself. That's usually 70 to 80% of your total images, because that's where the machine learning is training on what it's training. Then you have the validation data set. So when it's training, it needs to validate that it's actually going the right direction. So you give it 20% of those images, let's say, is the validation data set. And these two interact with each other through many iterations that we call epochs. And in the end, you have a test data set that's usually 10% or sometimes even less. And that's something that the detection model hasn't seen when it was training, when it was learning. And then in the end, you check how well it works with the test data set. So it might work well with your training and validation data set, but it might utterly fail on your test. And then you know that you have a problem because it's not general. And you cannot deploy it on larger data set. So this training took on one GPU 24 hours, and I used medium-sized network YOLO V8 with 25.9 million parameters. The training usually stops when it reaches some plateau in performance metrics that I will show in the next slide. And one of good practice is that I have 160 images, and I have to somehow select how I will separate them to these 3 different categories. So good practice is to permutate these categories, permutate these images, to see if your model was not just some random guess, but it's really robust. And also it can show you some potential problems. If some models are failing, you might see that something is wrong with your data. All right, so now let's talk a little bit about training performance evaluation. So we can track numerous metrics, but effectively in these object detection models, we have 3 main variables. One is true positive detections, TP. That's effectively you label a crater and then your detector detects the crater. It's a valid crater. This is what you want. Then you have false positive detections. So that's something that your detection algorithm labels as a crater, but it's not a crater. So it's false positive. And then you have false negative detection. It's something that was in the human labeled data set, but it was not found by the machine learning algorithm. You can also have true negative detections, but they are not in this. It's a possibility, but you usually don't have this in this task, because you would have to label something, some other feature that it's not a crater, and then the machine learning would somehow detect it as not a crater. You can do that, but we don't have to talk about it here. And then there are these traditional metrics. I will show you 3. So one is called recall, and it effectively shows you how many objects were recovered. So you have true positives divided by the total number of labeled craters, true positives and false negatives. Then you have precision. It effectively shows you how many false positives you have and how significant they are in the total data set. So it's true positives divided by true positives by false positives, plus false positives. And then you have F1 score. F1 score is a great number that gives you a harmonic mean between precision and recall. And effectively, it's this one metric that is quite well used in many different detection algorithms. So on the right side, this is a model of my training, the results of my training. So you can see that the machine learning trained for 1,000 epochs, and it started at precision 0, and it quickly got up to 0.6, and it slowly crept higher and higher until it reached, all these metrics reached around 80%. You might be surprised that it doesn't get 100% right. The precision is not 100% of recall or F1 score. And that's quite important, because you don't want to have 100%, because then it would mean that you overfitted everything. And it might mean that your model or neural network might not be able to generalize to unseen data. So this is great. It worked well. And I was happy with that, so I could continue with the crater detection on other unseen data. So what you can do, you can select images of your preferred area. So for example, you can go for lunar South Pole or North Pole, whatever region you want on the moon. And then what you notice is usually that the images don't have dimensions that of the training data set that you selected. For example, the LRO NAC images or the KPLO shadow cam images can be very long scans that can be tens of thousands of pixels. But you trained your network on quite a small image tile. It's 512 by 512 pixels. So what can you do? Well, it's quite simple. You can split the original image into these boxes that match your training data set. And then you have to add some overlap to those boxes, because you want to make sure that you don't have craters that are split into 2 different tiles, some edge cases, because then they would not be detected properly. Then you process every single segment separately, and then you put back everything together. Right. So you start with something like this. This is your little image. And then you have all these detections. And then you notice that there are so many different bounding boxes. It's not very clean. Many craters were detected more than once. And it's something that always happens. That's the nature of this object detection algorithm. So, and also it took only 1500ths of a second. So this is great, but it's not great enough. This is not useful because it's not usable. And what I want to mention as well is that every single of these boxes, bounding boxes, has a number. And that number is your how confident the machine learning algorithm is that this is a crater. So it can go from 0 to 1. Usually when I have some threshold around 0.3 or 0.5, depending on the data set you have and how precise your machine learning network is. And that gives you a great way how to decide how confident you are. This is something that you will never get from human labeling. It's always yes, no, or maybe. And I did this on my laptop, actually. So now you have multiple overlapping detections. What do you do? So there's luckily a simple solution called non-maximum suppression. It effectively removes all duplicates that have lower confidence values than the maximum confidence that's in a selected area. So it sorts all these detections that can be hundreds of thousands even for this image, and then set some threshold, and everything that overlaps within this threshold, the area, and has lower confidence than the highest scoring crater gets removed. And then you end up with something much cleaner. So you start with something like this. And after applying NMS, you end up with something like this. So for every crater on this image tile, you can see you have only one bounding box. It looks really, really clean. So the final number was 998 individual craters. I went through them one by one. There might be some that are not real craters, but it's then less than 1%. So you do this many, many times, depending how many images you have, and you process everything. And then you notice that your images might overlap as well, because the nature, because of the nature of the moon or whatever planetary body was scanned by remote sensing. But luckily, you have geolocated your craters, so you know where they are. And if you put together the entire database, you can again remove duplicates from the entire data set by using non-maximum suppression again. Then what you should do is to check a subset of your crater detections and decide if you are happy with that subset. You might realize that you detected a lot of craters that are not real craters, and then you might need to go back and rerun everything again, find where you made a mistake. But if you check a subset of your craters, let's say 10,000 craters, it's also much faster to check craters than to label them. Then you can call it success. And then you end up with a great data set, and you can do great science with it. So let's talk about the future a little bit. So now I showed you what can be done, and you can maybe asking yourself, why haven't we done the entire moon? Why don't we have 1 billion craters in our data sets? Why is there only a couple millions from the Robbins 2019 paper? And that's for multiple reasons. One reason is that currently a lot of groups are working on this, actually, and I heard that very, very soon you will have hundreds of millions of craters on the moon, and also other features like hollows, boulders, lava vents will be recognized and detected. And it's not just on the moon, it's everywhere. So in the next few years, we will have very big data sets for almost every single body in the solar system. There's also great benefit for citizen science with this, because we have so many craters that need to be validated. And what we can do it with citizen scientists that are numerous. We can have 10,000, 100,000 people looking at individual craters, and then it makes much easier to deal with billions of craters compared to a group of 10 people who would go crazy before they would even get to 1% of that database. Then also, in the future, we will have onboard machine learning driven algorithms that will detect features in real time. They will be trained with the data that we have today. And when the spacecraft is flying, it will already be detecting the the features in real time. So it will be done on board, and then it will be much easier to send data back to Earth because they'll be already processed. Another thing is, if you have great database of craters on the moon or any planetary body, and you can detect them from the spacecraft, you can automatically track spacecraft and rovers. You will know where you are anytime because you know what features you're looking at and you know where they are. And also, as one teaser for another work is that the digital elevation models, as I showed before, have very low resolution compared to the images themselves. That's because it's very computationally demanding to do these digital elevation models. If you focus on small areas like in Burton 2022, you can get much higher resolution. That's true, but it's difficult to do it for the entire surface. But there's a research that's happening in this field, and its aim is to enable, with the latest machine learning techniques, to the generation of digital elevation models in much faster way. Again, hopefully in a year or two, it will be available to everybody. So to conclude, today we learned that the machine learning already revolutionized numerous fields. I talked a little bit about AlphaFold, how it revolutionized medicine. We have large language models that maybe everybody on the planet now used ChatGPT at least once. We have Claude Gemini that help you with different tasks that it can teach you how to code or answer almost any question. I'm not saying that it answers correctly, but it will answer the question definitely. We have also object detection. I showed you that it works on the moon, it works in cars, it works on planes, everywhere. The applications are limitless almost. Then we showed that machine learning was already applied on the moon very successfully. So until recently, we have 2 million craters from Robbins 2019. It's a great database, and I'm really happy that we still have it. But we have already a large data set on Mars, 90+ million craters from Legain 2022. And as I said before, Mercury and the moon will very soon follow, and we will have hundreds of millions of craters on the moon and tens of millions of craters on Mercury as well. Also, one of the great things about machine learning and this science is that all the necessary tools and datasets are already available. You can go to GitHub, Zenodo, and Planetary Data System, and you can download anything you need to start with this today. And everything is so well documented that there should be no problem for you to get into it right away. It's also great that today the computational power and the codes are so efficient that you can do this on a single laptop. You don't need huge server or hundreds of GPUs to do this. These tasks that I've done here are quite simple compared to what big companies like OpenAI are doing. And it can be done on a single laptop. Thank you. We have a great future ahead of us, and I cannot wait to see more. And this is the end of the talk.
Yeah, thank you, Dr. Pokorny, for such an engaged talk. So I think it's time for the QA session. So does anyone have any question? And please feel free to turn on your microphone and ask Dr. Pokorny. Here I saw one question from the Dr. Ian Lai. He say, "Hi, Petr. Thanks for the nice talk. 2 questions. The first question, can we know the depth of the craters? This is the first question. And the second question is, how do these craters link to the lunar meteorite impact environment?"
That sounds great. So first, let's talk about the depth of craters. So if you have the digital elevation model, that gives you the depth of the crater right away. But the problem is that you have low resolution, so you cannot get depth of craters that are tens of meters or hundreds of meters because the digital elevation models at the moment are not high resolution enough. What you can do, what we are trying to do actually, is I'm working on it with a group of people at NASA Goddard, is that we are trying to figure out how to get the depths of craters only from images. So we will use a synthetic digital elevation model, generate the images that we would see based on the illumination, and then try to get some idea how to get the depth of the crater from that. So there's work in progress. If you have DMs, digital elevation models, you can get the depths right away because it's the 3D representation of the surface. But hopefully in the near future, we will have that similar capability from images themselves. And as to the relation of these craters to bombardment of the lunar surface. So these craters down to tens of meters are created by impactors that are at least 1 meter in diameter. So these are usually near-Earth asteroids from the main belt that evolved slowly and then started impacting the moon and the region around Earth. There are multiple papers. One paper, for example, from Grunwick 2018, gives you the model for the near-Earth asteroids. So that's a great way to get a population that's have potential to impact the moon. And then there was a series of papers by Robertson and then Lagane that looked at what is the imprint of that near-Earth asteroid model on the moon. So we have nice connection between these two populations, and it matches quite well what we see on the moon and what we can model from the main belt escaping populations. As for meteoroids, it's a little bit more difficult because meteoroids are usually smaller and they create much smaller craters that we usually cannot see from this remote sensing. So only thing that we can see with meteoroids is the dust exosphere or the dust cloud that envelops the moon, and that was detected by LDEX instrument on LADEE spacecraft, and that the shape of the cloud is quite asymmetric, but it matches well with the meteoroid model that I created in 2019. So that's been solved as well. So I think we are pretty good at predicting the impacts on the moon from these two populations.
Okay. So any other question for Dr. Pokorny? I have a quick question. Do you have any plan to apply this algorithm to other bodies such as the Ganymede or the Callisto? Because I know that the Callisto also have many craters on the satellites.
So once we get it working really well in the inner solar system where we have much more knowledge, we will definitely go to Ganymede as well and the Callisto. Those are great targets, and I hope that we will be able to use the same algorithms that we have on the moon and just quickly get some basic preliminary data on Ganymede and Callisto, and then build from that something more specific to those two moons that are super interesting. So it's very possible. Like, there are almost unlimited possibilities today. So just can't wait to have more time to do more do more research in this area.
Okay, so thanks for your answer. And any questions? I have other questions because I'm not the expert of the machine learning. So you mentioned that in the process of training the crater detection algorithm, we can track various evaluation metrics like the recall, the precision, and the F1 score. So how can we use these metrics to assess the performance of the model and ensure the reliability for the result? So, and you also mentioned that if the F1 score drop below 0.7, and what's the potential issue might this indicate, and how should we adjust the model to address this problem?
That's a great question. So when I first trained this method, algorithm, I had a data set that, I thought it was great, but then it didn't perform well. The precision was below 60%, the recall was also bad, and the F1 score also was 0.6. Then I noticed that there are several images that had higher noise than what I expected. So it was sort of confusing the machine learning. It was thinking, it saw craters that look quite different, and it was not performing well. So I removed those noisy images that didn't appear in my dataset of images I was going to process. And first, these metrics increased a lot to, you can see, 80%. And it also made more sense that the machine learning is taught from the training data set. So the more you confuse it, the worse it will perform. So it's very important to have the best data set you can have effectively for the training. Another thing that helped was I played a lot with these the augmentations of the data set. I tried I effectively created several permutations of different variables and tried how each transformation that we show here impacts the score. So I noticed that something like blurring, for example, was decreasing extremely significantly the performance of the network. So I stopped applying blurring, for example. So I was sort of learning how to enhance my data set and how not to make it even worse. So there are multiple things that you can tweak, and it's a learning process. But effectively, you should strive to have the best data that you can have for training, and try to give it as much variety as possible. And also, one thing is that you might have mislabeled some craters, for example, or some other features. So if the labels are not great, or if the bounding boxes are not good, then it will also get confused, because if some of the bounding boxes are too wide and some of the bounding boxes are too small, then it just cannot grasp what you want from it. It's like teaching a little kid, if you confuse it, then it will get more and more confused and will not learn anything.
Yeah, I think it's really, really interesting issue. So maybe I can read more book or some paper for more understanding about this.
There's almost infinite amount of information today, because everybody's trying to do this on so many different fields. So it's great.
Okay, here I see other question. Oh, thank you for answering. And I see other question from the Yara Subade. So hello, Pet. Aside from image, can 3D point cloud format can be used as a sample for the data set? If it can, what machine learning technique be possible for it?
Interesting. So you would want to use the 3D representation of the surface itself, yeah? Am I understanding correctly? I cannot see you, so I just see my slides. To be honest, I'm not entirely sure, because these image detection techniques are usually for 2D imagery, but you can add another dimension there, another set of information. So, for example, in the DMs, you have the depth of the crater. So if it's positive, if the crater goes up, so that means that it's not a crater and it's a boulder. It could, and you can use that from what we see from the 2D images. Sometimes it's very difficult to distinguish between a boulder or crater if you don't know the illumination angle. If you know it, then you can tell the machine learning, the algorithm, if the shadow is on the wrong side, it's not a crater, it's a boulder. So there's things like that. It can always be augmented, the algorithm itself, for something new. So there are ways how to do it. It's usually non-standard, so you have to apply some coding and adjustments to the code, but everything is possible effectively. Also, the more information you have, the more precise it's going to be, because it's going to be looking for things that are more certain. So it's a great idea. But honestly, I don't have much experience with that, so I cannot guide you to a very specific technique that you could use.
So is that okay? Yara Subade? Yeah, okay, I see. So any other question? I think it's about the time.
Okay, so I'll stop sharing so I can see you all. Awesome.
Okay. So if there are no more questions, I think it's about time. So let's once again thank Dr. Pokorny for today's talk. Thank you very much. And we have another online talk on September 12th. So please visit our website for more information. So thank you all for joining us today. And we will see you next time. And thanks for Dr. Pokorny. Thank you. Thank you very much.
Thank you.
Thank you. Bye-bye. See you.
Thank you. Bye.